So for Unit 4, we're going to be talking about systems of equations, and specifically systems of linear equations. So the first definition that we're going to talk about is what exactly a system of linear equations is. And it's very simple. It's two or more linear equations. So the definition of a system is two or more linear equations. So that means that they're on the same graph. That means that when we solve them, the solution has to satisfy both equations. An example of this would be y equals 2x plus 4 and y equals x plus 2. So it's two linear equations that are graphed together. And usually we recognize that it's a system because they'll have the one curly bracket connecting the two of them. So you guys are going to get to practice your curly brackets in this unit. So let me do it again for you guys. You start at the top and kind of swoosh it out like almost an S, and then you do the same thing backwards. Okay, so the curly bracket indicates that they go together. So that's usually how we can tell that it's a system. Your textbook does not always use the curly brackets, but the two equations will be stacked on top of each other. I always try to use the curly brackets because it's a little more mathematically correct, in my opinion. But it doesn't always, so just be aware. So then what's a solution to the system? A solution to a linear equation is an ordered pair, right? We did that very first day of Unit 3. So a solution to an equation is an x comma y or an ordered pair that lies on the line, any point on the line, yes? And any point that makes the equation true. So with a system, it is any ordered pair, the solution is any ordered pair that makes all of the equations in the system true at the same time. So I want you to underline, highlight all. Okay, and that means that it has to make the equations true at the same time. So usually a system most often only has one solution, and we're going to look at what that means graphically today. So for the system that's given above, y equals 2x plus 4 and y equals x plus 2, it actually only has one solution, and you guys are just going to take my word for it today. But the solution is the point -2, 0. Okay? So if I were to take the point -2, 0 and plug it into the first equation, y equals 2x plus 4, I would get a true statement. And if I took -2, 0 and plugged it into the second equation, y equals x plus 2, I would also get a true statement. So I'm looking for a true statement for both. Graphically, let's think about it. If I have one line that's going, I don't know, if I have only one point on one line that's true for the other line, what do you think it will look like? So let's say I have a line that goes like this and a line that goes like this. Where do you think the solution is going to be? Right where they cross. And that's what we're going to talk about today. Okay, so turn the page to lesson 1. We are going to solve systems of equations only by graphing today. So that's all we're doing today. One thing I want you all to be aware of. Please notice that in the examples that I give you, at least these first three, they're all in slope-intercept form. That's not always the case, but for the sake of time today, that's what we're going to be doing. But sometimes you might use x and y intercepts. Sometimes it might be in point slope form. Sometimes you might want to convert the equation to slope-intercept. So it's not always going to be super cut and dry, but I don't see the point in having you guys do all that tedious stuff right now in class when nothing changes. I mean, you're still always going to graph it and look for the intersection point. So we're going to do number 1 together, and then I'll have you guys do 2 and 3 on your own. So I'm going to use 2 different colors for each of the lines. You can if you want. If you don't have colored pencils, that's fine. Y equals 2x plus 4. Let's graph that. What is the y-intercept of that equation? Good, 4. 1, 2, 3, 4. And so I'm going to put a point. And the slope is positive 2 over 1. So I'm going to go up 2, right 1. And I like you to do 3. So what's the opposite of up 2, right 1? Down 2, left 1. Good. And then draw a line as straight as you can. Oop. Here, let me try this. I would suggest that you use some kind of straight edge to graph your lines, and make sure you extend them all the way. Because if you are not extending your lines all the way through the graph, you might not see where they intersect. So use the side of your ID card, the side of your binder, a ruler. Use something to get them straight, because if your lines are not straight, you will not see the intersection very clearly. So then let's do this second line. Y equals x plus 2. The y-intercept is 2. And the slope is 1. So I'm going to go up 1, right 1, and down 1, left 1. I'm going to try this again. And this way. Okay, I think that's correct. Okay, and we're looking for the point of intersection. Yeah, I did not graph it very well. And it's the green line, not the blue line. So let's try the green line again. There we go. Okay. So what I want you guys to do, where do you see them intersect? Yeah, it should be at -2, 0. So that point is your solution. So the solution of this system is at the point -2, 0. So what issues do you see with using graphing as a way to solve a system? Yeah, your line with graphing, while we do try and be as accurate as possible, when you are graphing by hand, it's not always the most accurate. If I'm using Desmos to graph a system, do you think it will give me an accurate line every single time? Yes. But since we're doing some of these by hand, graphing is not always the best way to solve a system, because you're graphing, as you saw from my own graphing, I knew what the answer was supposed to be. So I knew that it was not crossing in the right place. That's why I really want to encourage you, when you are doing your homework tonight, use some kind of straight edge to make your lines as straight as possible so that you can be as accurate as possible. How could I check that this point is correct? Plug them into the equations. You should get a true statement for both, because this point is supposed to lie on both lines. Does that make sense? So it should be true for both statements. What I want you guys to do right now is try numbers 2 and 3 for me. Be as accurate with your graphing as possible. Okay, so for number 2, y equals 2x minus 1. How would I graph that? David, how would I graph y equals 2x minus 1?
You go down 1 on the y-axis.
Okay.
And then for the rise, you go up 2.
Mm-hmm.
And then 1 to the right.
Okay.
And then you go down 2.
Mm-hmm.
And then 1 to the left.
Perfect. Okay, so then we would draw a line, and I'm going to try and do this as straight as I can. 2 over 1, up 2. Okay. And then this would be down 2, left 1, down 2, left 1. Okay. So there's the first equation. Second equation is y equals negative 2x plus 8. How would I graph that one, Christian? Okay, so I would start at 8 and then go down to over left or right? Right 1. And I want 3 points, but if I go the opposite way, it goes off the graph. So then what did you do? Okay, so he went down 2 and over 1 more. And I'm going to do my best, guys. I think that's it. Okay. So then what I want you to do is let's look at where they intersect. They actually don't intersect on a grid line, which is a problem for us. So that means we have to estimate, which is another reason why graphing is not always the most accurate. Approximately where on the x-axis does that one look like it comes down? Does it really go halfway through, though? It's not even exactly in the middle. So I would say 2 1/4. So 2.25. And then the y does look like it's in the middle. So what would you call that one? 3.5. Yeah. Do you see why graphing is still not the best option? That can be a real pain. So I put that one in there on purpose so that you guys are getting used to it. But let's do the other one. I think it comes out nice and whole. Y equals 1/2 x plus 7. So you should go up 1, 2, 3, 4, 5, 6, 7. And then down 1, right 2. And then up 1, left 2. So my line, down 1, right 2, so it goes like this. And this one goes up 1, left 2, so it should go through that one. And then my blue one, 3 over 2x plus 3, so I'm going to go up 3 and then up 1, 2, 3, right 2. Oh my gosh, that's convenient, right? Because look what happened. It just so happened that in counting my slope, I hit the other line, right? David? Did I? Oh my gosh, you guys. Let's go back. Thank you. Teachers make mistakes. I go up 1, right 2. There we go. Down 1, left 2. So right there. Okay. That looks more. You know what? On my answer key, I did the exact same thing. And I had to white it out. It's embarrassing. Okay, so I go up 1, right 2, up 1, right 2. And then down 1, left 2. Okay. There we go. And then the blue one, now it's not going to be quite as convenient. 1, 2, 3. And I go up 1, 2, 3. Right 2, so right here. And then down 1, 2, 3. Oop. 1, 2, 3. Left 2. And they're going to cross here. Okay, so when I graph it, I end up getting this line, and they cross just barely on the graph at that point, which is what? What's that chord? Who can tell me? Jen, what'd you get? 4, 9. Okay. So you have to make sure that your graphs are as accurate as possible. And if that means plotting more than just 3 points, plot more than just 3 points. Okay. Okay, let's look at what this means. Are we good so far? Everybody? Okay, let's look at what this means in terms of writing and graphing a system in a real world situation. In writing a system of equations. It's very similar to what you did in Unit 3, but this time there's 2 things you have to be aware of. So they give you more information, basically, to be more accurate. So number 4, one satellite radio service charges $10 per month plus an activation fee of $20. I think that's important. I'm going to underline it. A second service charges $11 per month plus an activation fee of $15. In what month will the cost of the services be the same? So basically, I want to know how many months need to pass before they cost the same or before the 2 equations cross. So let's write an equation for service 1. Let's write an equation for service 2. We're going to are you guys want to use X's and Y's? Okay, so let's let Y equal the cost, total cost, and X is going to equal number of months. Okay. Are we going to use the same X and Y for both equations? Yeah. Yep, the same variables. Because it's a system, X stands for the number of months for both equations. Y stands for the total cost for both equations. So the variables and what they represent do not change for different equations in a system. So if I'm charging $10 per month plus an activation fee of 20, that first equation is going to be Y equals 10X plus 20. So $10 per month plus $20. And then I'm actually going to change the colors here. I'm going to use orange for the other one. The second equation is going to be Y equals, how much do they charge per month for the second service? 11. So 11X plus, what's the activation fee? 15. Okay, so then my next question, do you think that the scale, 1-to-1 scale on here is going to do it for us? No. Along the x-axis, first we need to label it. So the x-axis represents what, guys? Months. So x-axis is going to be number of months. And I know there's not a ton of room. So just write small. And it's not going to take that many months for these 2 to cross. So I'm actually going to let each line represent the half-month mark. Okay, so every other is going to represent 1 month. So here's how I would write that. I'm just going to put a dash at every other and label them 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So every other dash is going to be a month. That's going to help our graph kind of spread out a little bit. And on the y-axis, that cost is going to start growing pretty quickly. So I am going, let me see. I'm going to let every mark be 5. So I'm just going to mark every 10. So that's 10, 20, 30, and that's going to go all the way up to 90, 40, 50, 60, 70, 80, 90, and then I forgot to do something. What did I forget? I need to label the y's. What does the y represent? Total cost. Okay. So let's graph the purple one first, 10x plus 20. My y-intercept is 20, so I'm going to put a point there. And my slope is 10. So I'm going to go up 10 to 30, right 1, which is going to end up being right here. So when you are choosing different scales for the x and the y axis, it's totally okay. You are allowed to do that. You just need to make sure you're paying attention to what the scales actually say. And I'm going to graph one more point. So I'm going to go up 10 and right 1 more. So my graph is going to look like that. And I'm going to try and draw as straight a line as I can. Oh, that's a different color. So up 10, over 1. I think I got it. Okay. Okay. Everybody with me? Okay. And then y equals 11x plus 15. So my intercept is going to be at 15, which is pretty easy. But then 11 is where it gets a little tricky. So I'm going to go up 10, which puts me at 25, and just a little bit over. And then over 1. So my point is actually going to be just above the 25 mark. And then I'm going to do that one more time. So I'm going to go up 10 and then just above. So up 10 more and then just above. So now I'm going to be at 37. Oops. But then over 1. So right here. And then try and graph that as best that I can. These end up being really, really close. Okay. So, you guys, mine does not come out. Yikes. Let me try that again. There. Okay. So it's pretty cost effective to choose plan 2 for a little bit, right? And then it gets too expensive. They should have crossed at 5 months. Okay. So this is, once again, I don't know if I can say this enough, why graphing is not always the best option. Now on your homework, if you get something that comes out this like close, maybe get on Desmos and graph it and see what it says, but it comes out to 5 months. Okay? So it's nice that I know what the answer is supposed to be. Okay, number 5 is very similar. It's 2 trees growing at different rates. We're going to skip it for right now. We'll come back to it maybe tomorrow as a warm-up. But let's talk about infinitely many and no solutions. Okay. So it does happen that sometimes when you graph systems, there are going to be no solution or sometimes what we call infinitely many solutions. So I want to make sure that we go over it. So let's look and graph these really quickly just so we can make sure that we get it in. Y equals negative x minus 3. My y-intercept is at negative 3. And my slope is negative 1. So I'm going to go down 1, right 1, or up 1, left 1. Okay, and then my other line is at negative x plus 5. So I'm going to go up 1, 2, 3, 4, 5. And then same thing. Down 1, left 1, up 1, down one, right one, up one, left one. And when I graph these, what do you guys notice? Tell your neighbor what you notice. Rebecca, what did you notice? They're parallel. So will they ever intersect?
No.
Never. How could we have determined that they were parallel? Yeah, they have the same slope. Before we even graphed it, you should have known they were parallel. Parallel lines never intersect. So will they ever have a solution? No, the solution is where they cross. So parallel lines have no solution. And you can do the 0 with the dash through it. Okay? Yeah, that's fine. Okay, so let's do this last one really, really quick. Y equals 3x minus 3. That's going to go down 3. And then my slope is up 3 over 1. 1, 2, 3 over 1. So we graph it. Okay, the second line is not in slope-intercept form, so we want to put it in slope-intercept form. What do I need to do? I already have the y by itself, but there's a 3 attached to it, so we're going to divide both sides by 3. And that gives me y equals 9 divided by 3. 3x minus 3. Okay, what's going to happen when we graph that? What do you guys notice? It's the same line. Ooh, that's definitely not right. It's the same line. So how many times does the purple graph intersect the blue graph? Always. So we call that infinitely many solutions. Okay? So they always are touching. There's a summary at the very bottom of one solution, infinitely many solutions, and no solution. So if they cross, it's 1. And then same line and parallel lines are infinitely many and no. Okay?